So if we're talking about ions, they gain or lose electrons to become noble gas configuration. All right, so magnesium 2 plus gets to be neon, or oxygen 2 minus gets to be neon. So this is actually for main group. So there's some other things here. So what if it is a transition metal or has an intervening D block? So there's a kind of this is a special rule. Or I mean, it's not exactly special, but when removing electrons, take away the highest N electrons first. So just why is that a special rule? Because it's different from the filling order. Okay. Is everyone on board? Is this cool? Are we all right?
Yeah.
All right. So how about titanium 2 plus? So in order to do titanium 2 plus, first let's look at titanium. What's the electron configuration of titanium? If I look at it here, it's going to be the noble gas before it's argon, and then 4s2 3d2.
Mm-hmm.
So titanium is argon 4s2 3d2. And so technically when it forms an ion, titanium 2 plus would then, I would remove not the D, which was the last electrons I put in, but I would remove the higher energy level. I'd remove the S. So titanium 2 plus is going to be argon 3d2. And so they kind of skipped that on the PowerPoint. They gave you nickel and they didn't explain it, remember? So nickel was argon 4s2 3d8. What's nickel 2 plus going to be?
Argon 3d8.
Argon 3d8. So that as an ion, remember that the S and the 4s and the 3d are very close in energy. And as an ion, that D shell drops in energy. So it becomes the place to be, 3d8. So that's what they did. They didn't explain that. So I wanted to explain that to you. In some cases, it makes a lot of sense. Also, let me just put that down. Okay. Also, what if you have to lose more? How about iron 3 plus? How would we do that? Well, first you do iron, which is argon 4s2 3d6. Aha. So how would we do iron 3 plus? What am I going to take away here?
First the 4s2.
Yeah.
And then
I take the
from
4s2
3d6.
and I get 3d6, but then up 3 plus, I got to take away one more electron, right? So what would it actually be?
Argon 3d5.
Perfect. And so sometimes the transition metal ions will, the way they react will be to either get an empty shell like titanium, or to get a half fill. So let's actually show that. This is, we got an, oh, I guess we didn't quite do that. Titanium 4 plus would be an empty shell. But they try to empty their D if they could get a D0. So actually, well, we could do one of those, like scandium. So let's do it. Let me just write next to it. Scandium would be argon 4s2 3d1. Scandium 3 plus would just be argon. So transition metals can either have an empty D or a half D. Now, a lot of times they can't get to empty or half or full. And let's do zinc. So zinc is let's do argon first. Argon 4s2 3d10. So it's remember, zinc was one of the always cations. Zinc is always zinc 2 plus, which would be what?
Argon 3d10.
Yeah, and argon 3d10, I've finished the third energy level. That's very, very stable. I've you know, because technically in the third energy level, I can have an S, a P, and a D. And now I've filled all of them. There's no 3F. So this is having a full D. Let me put that in parentheses. These are not answers. You should, but these are kind of strategies, but you won't always get it. Like nickel doesn't get to have a full D. It just gets to get rid of the S. Same with titanium. Doesn't get to have an empty D. It just gets to get rid of its S. So they can't always do that. But a lot of times they'll react in such a way as to get an empty D if they're close to the beginning of the D block, or a half-filled D if they're somewhere in the middle, or a full D if they're toward the end. So that's kind of what transition metals do. I'm spending a lot of time with this, which is probably fine. One last example. How much time have we got? Is it counting yet? Or is this brand new?
It's not counting yet.
It's not counting yet. So we still have a lot of time. Let's do lead. What about lead? So I was mentioning lead earlier. Let's just do lead first. So lead is xenon 6s2 4f14 5d10 6p2. So there's two. Lead basically has two situations. There's lead 2 plus, which would be what? What would I do? I'm not going to touch the noble gas. What would I get rid of?
The 6p2.
I'd get rid of the 6p2. So I'd have 6s2 4f14 5d10. Basically, these ones join the core when they, you know, so that's it. And then lead 4 plus would actually be more stable. That would be the best case scenario. Xenon what?
4p.
What would I get rid of next?
6s2.
I'd get rid of the 6s2 and I'd have 4f14 5d10. And so this is actually what they call a pseudo noble gas configuration. It's pretty stable, right? Because the main group elements will get a full, like sodium gets sodium plus. Let's do sodium plus gets to be neon. That is essentially noble gas configuration. Lead can't get noble gas configuration because it would have to remove another 24 electrons. So lead gets something that's quite stable called pseudo noble gas configuration. Excuse me. Okay, So that's ions in a nutshell, right? Let's continue on. Are you guys ready to continue on? All right.
Yeah.
All right. Is this making sense to everyone? Is it okay? So
Yes.
it's just a small rule, and I think it makes sense when you look at what you end with. The next idea is called periodic trends. And these, if you get these are really easy test questions. So here's my, okay, so I want everyone to say back to me. Can you say up and to the right? Can you guys repeat back, up and to the right?
Up and to the right.
Okay, and that's the trend. And actually, if you want to be technical, if you have a conflicting, like one element's up and the other one's right, I'm going to use a bad word, up will trump going to the right by at least one or two elements, okay? So up is a bigger difference. So let's look at, here's my bad drawing of the periodic table. Can I draw a periodic table? Is that okay if I?
Mm-hmm.
All right, here we go. I'm drawing a periodic table. All right. So as I go up and down, so in the first energy level, there's only one shell, right? In the second energy level, I have two shells. In the third energy level, I have three. When I get way down here, I have 7 shells. So you can see how that's really going to affect the size, right? As I go up, it's going to get smaller. Yeah, that's going to be one of the trends. Okay, so as I go up, I have less shells or energy levels. And that means the nucleus is more exposed also. All right? So what happens as I go to the right? As I go to the right, I get more protons. What's going to happen when I have more proton pluses? So let me show it down here. Maybe this is too crowded. Or actually, no, let's just imagine this is the second period here. I have two shells like this with, say, well, the first element in the second period would be lithium, right? When I get over here to neon, I still have two shells, but they get pulled in really tight, smaller. Because over here I have 10 proton pluses. Over here, let's just imagine lithium, I have 3 protons, right? So if neon has more than 3 times as many protons, it's going to pull all those electrons, shrink. How do I show that? Here, like that. Okay, so big. Let me show that down here. So going across second period. So I'd have a really big 2, right? And then it would get, as I have 3 protons, as I have 5 protons, maybe it gets a little smaller. As I have 7, let's say 8, I don't know. Okay, 8 protons, maybe it gets a little smaller. And then when I get to 10 protons, much smaller, yeah? Does that make sense? So the electrons get pulled in by the protons. You can think of it like having a bigger force of gravity. You guys think of gravity? I know maybe that's not good to use another scientific concept to talk about a scientific concept. But if you have a big star which has a lot of gravity, the orbitals, that planets will be pulled in closer, right? If you have a star that has weak gravity, not as strong of an attractive force on its planets, the orbits would be wider. And the same thing is true for the electrons. So let's go back. So again, as you go up, you have less shells, nucleus is more exposed. As you go down, you have more shells. As you go across, you get more protons. So the more protons have a stronger pulling force. Okay. And so this is the up and to the right. Yeah? Okay. Let's continue. Okay. So I'm going to draw a smaller periodic table and talk about the different trends. Okay. So okay. So as I go up and to the right, atoms will have a smaller radius, which means they'll have a smaller volume. They'll also have a higher ionization energy. A higher electron affinity. I'm going to have to define all these in a sec. They will have a higher electronegativity. That's technically in the next chapter, but it follows this trend, so I wanted to mention it. They tend to be more like a non-metal in behavior. They'll tend to gain electrons instead of lose electrons, et cetera, et cetera. Okay. All right. So, and actually in Chem 1A, there's more than these, but all of these things happen as you go up and to the right. As you go down and to the left, so if I go down, I'll write that actually. If I go down left, then I have the opposite. I'm going to have a larger radius, larger volume, comma size, a lower, I'm going to abbreviate it. So ionization energy is IE. Lower electron affinity is abbreviated EA. A lower electronegativity, EN. And you tend to be more like a metal. You tend to lose electrons. Okay? So that's the whole idea. Maybe at this point, this might be a good place to define some of these things. I'll run the PowerPoints too, but we might as well write this out. So I'll just move this down a little bit. Okay. Ionization energy. Abbreviated IE is the energy to, let's not underline that, to energy to remove 1 mole of electrons from, I'm sorry? Question? So the energy to remove 1 mole of electrons from 1 mole of gaseous atoms. So or ions. So I heat an element up till it's a gas, and then I calculate how much energy does it take to pluck 1 electron off each atom. So we'll look at that. The electron affinity EA is the energy change and this should be said in kilojoules accompanying the addition of 1 mole of electrons to 1 mole of gaseous atoms or ions. One other thing to say about electron affinity is it's kind of a rough trend. It's not as beautiful as some of the other ones, like the volume. Oops, rough trend. Okay. But again, they take 1 mole of atoms, they heat them up till they're a gas, and then they add electrons and they look at the energy change. And even though this one's in the next chapter, I want to define it. The electronegativity En is the relative, and how they measure this is, I'm not sure exactly, but use this chart for eons, is the relative ability of an atom to attract shared electrons. So meaning if I have electrons in a bond, right? So like hydrogen and chlorine. And so which atom has a stronger pull? Let's see if I can pull question mark. And the last thing to say about electronegativity is noble gases are excluded because they don't tend to want to make bonds and gain electrons. So they're excluded from this chart. Okay. So let me go to the PowerPoint, I guess, at this point. Okay. Can you guys see the screen again? I just have to check.
Yeah.
Oh, good. All right. So let's go to, oops. Missed something? There we go. Periodic properties. Okay. So let's just kind of run through. So electron configurations are related to the following properties. Relative reactivity, how reactive an atom is, right? Ionization energy, the tendency to lose electrons. The atomic radii, which also, the radius is exactly proportional to the size, right? The volume, if an atom is a sphere, you guys remember from geometry, the formula for the volume of a sphere, it's 4/3 pi r cubed. So a small change in a radius equals a big change in a size. Maybe I should, oops, well, okay. Did I go back? Okay. So we talked about the activity series. The most reactive metals are the most down and to the left on the periodic table. The least reactive metals are the most up and to the right, essentially. So we see that the most active metals are those in the 1A and the 2A, really far to the left on the periodic table. The more active the metal, the more easily it loses electrons. So remember, if it was a competition between two metals, the calcium would force something lower than it to gain its electrons. Calcium would give its electrons to zinc, and zinc would have to take it. Or zinc would give its electrons to nickel, and nickel would have to take it, and so on. All right, so that chemical reactivity. And this is just the reactivity of metals. There's a corresponding activity series that we didn't cover that has to do with the halogens. So the more up and the right, fluorine would be more reactive than chlorine, and chlorine would be more reactive than bromine, right, in a similar style and fashion. Okay. So alkali metals form +1 ions since they only have one valence electron. So you also see these patterns too, right? There's patterns of reactivity. All of the 1A metals form a 2-to-1 ratio with oxide, right? Li2O, Na2O, whereas all alkaline earth form a 1-to-1 ratio, MgO, CaO, SRO. So the patterns of the ionic compounds they form, it's very predictable. This is showing periodic properties of actually all of the 1A metals react very violently with water. They actually catch on fire in water, which is really impressive to see. We can show a video, but again, there's no sound. If you guys want it, I could link a video for this. But this is showing the idea as you go down. These are all 1A, right? Lithium is in the second period, sodium's in the third, hydrogen fourth, rubidium fifth, cesium sixth. As you go down, they get more reactive. If you look at cesium, it's basically exploding when it hits the water. Whereas when sodium hits the water, it's going to think for a while and then it's going to catch on fire. And then sodium's going to just kind of fizzle, not as reactive. I mean, they all react quite vigorously with water, but that trend as you go down, it becomes even more pronounced. But all 1A metals react with water to form a metal hydroxide and hydrogen. And then the hydrogen gas, because so much energy is being released, the hydrogen gas reacts with oxygen. You get this violent reaction. Okay. We mentioned ionization energy, and we wrote it down. Ionization energy is a measure of the energy required to remove a valence electron from a gaseous atom, and specifically 1 mole from 1 mole. So I take an atom and put it in the gas state and then measure the energy change when it loses an electron. So metals will have low ionization energy and non-metals will have higher ionization energies. And that follows that same trend. So this is actually, if you guys can see this graph, this is showing ionization energy, right? Cesium has the lowest ionization energy on the periodic table. Helium has the highest, right? Because it's the atom that is the most up and to the right, right? So again, as I go up the periodic table, there's less shells. So if there's less shells, I think I can draw that. Let's annotate. Okay. So again, up here, there's less shells. 1 shell, 2 shells, right? And so if there's only 1 or 2 shells, then the protons in the nucleus are more exposed. And the electrons will feel the pull of those protons with more power. As I go across the periodic table, I get more protons. So if I look from lithium going up, it looks like almost like a ladder. Now there's some places where I go down. Like if you look lithium, I go up to beryllium. I slightly down to boron, but then I go up to carbon, up to nitrogen, slightly down. So it's a trend. It's not a perfect trend. The trend going across is a little jaggedy. If you look at the trend going up, look at the purple. So it's up, 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 up. So going up is basically a perfect trend, okay? We have 10 minutes at this point. Let me go back to mouse, okay. But anyway, so that's, so non-metals that have very high ionization energies are never gonna lose electrons. It's gonna be, not in nature, not in a natural reaction. It would take some weird artificial process to pluck an electron away from fluorine or helium, right? But the metals down here with really low ionization energies can lose electrons in nature. They can get stolen by something that has a very strong attraction, right? And if you look at like selenium, arsenic, silicon, though tellurium, they basically have an intermediate ionization energy, right? The differences between being a metal and a non-metal and a metalloid is, you know, basically a difference in ionization energy and some other of these periodic trends that we'll see. Okay, let me erase this and we'll go to the next slide. Okay. All right. So ionization energy increases as you go up and to the right, right? So again, it has to do with the shell size. As you go up, you have less shells, and the electrons, the outer electrons fill the pole of the nucleus more. As you go across, the shell shrinks and gets smaller, right? And that's the basic idea going on here. Let's continue. Okay, so for these, you just have to look at the periodic table, and maybe we should write these, I should write these down, or we could look, because I want to kind of show the periodic table. Let's do magnesium and calcium. Well, which one's more up and to the right? Calcium and
Magnesium.
magnesium. Which one's, I'm sorry?
Magnesium.
Magnesium, yeah, they're both in the 2A. Magnesium's higher, so magnesium's going to have a higher ionization energy, right? So these are really easy test questions if you get the trend. If you can just say up and to the right, right? Okay, so that one was easy. Okay, let's do another one. Oxygen or fluorine? Aha. So,
Fluorine.
yeah, why did he say fluorine? That's correct answer. Let me put text in here. Hold on. So magnesium is up. Fluorine is to the right. It has more protons, right? Magnesium is up. It has less shells. So the electrons in those shells are held more tightly. Yeah? Okay. What's the next one gonna be? Let's go back to mouse, I guess. Okay. Ah, silicon or fluorine? Which one's gonna be?
Fluorine.
Fluorine. Well, fluorine is both up and to the right. Yeah? Okay. It's pretty easy, huh? What happened? Okay. I thought we saw this slide already. Ionization energy decreases as you go down and to the left. You have the opposite trend, right? So this is what why is cesium so explosive when it reacts with water? Because it's really easy to pluck off an electron. It doesn't take a lot of energy to break that electron bond, and when you form these products, you give off a lot of energy, right? It's a really interesting reaction. Let me erase here. All right. There's also an idea of what they call successive ionization energies. So in general, the first can you guys see that down here? Let me show that text. So this thing right here, the first ionization energy, IE1, IE1 equals first IE, right? And then IE2 equals second ionization energy. So in general, so the first ionization energy would be removing the first electron, and it's not shown on this chart, I guess. That was back a slide, I guess. Maybe it was like, I think the first ionization energy, so I don't have to go back a slide, was around, did I do that right? Shit, there we go. Around 700 kilojoules per mole. Let me move that over. Right? And then, so that's the energy to remove the first electron. And then then we get magnesium ion showing up here. Can you guys see where the cursor is? And so magnesium ion losing a second electron, going to magnesium 2+, well, that takes about twice as much energy to remove that second electron. Why would it take more energy to remove the second electron? What's going on? Well, magnesium has 12 protons. So as I lose electrons, the electrons I have left are held more tightly, right?
Yeah.
So it doubles. It doubles. But now let's look at the third ionization energy. What happened with the third? So now I have magnesium 2+, and I'm going to remove a third electron and go to magnesium 3+. Now, does magnesium 3+ exist in nature? What's the normal ion of magnesium?
Mg2+.
Magnesium 2+. So look, there's a huge energy jump. It's 7,733 kilojoules. So if we're going from 1,400 to 17, that's a five-fold jump. Why 5 times jump for IE3? What's going on? Why is it such a big jump? Anybody think about that? So we're removing core electrons. And so when we remove core electrons, right, magnesium 2+ has got the electron configuration of neon. When I go to magnesium 3+, I'm removing those core electrons, and that's very costly. They're super stable, right? So that's kind of the idea. Let's go back to mouse. Okay, I'm going to continue. I'm going to run out of time in a minute here, but let's see what happens. Okay, so this is showing the pattern, actually. Let me erase that from before. So if you look at lithium has a low, can you guys see lithium at the top of the table? It has a low first ionization energy, then there's a big jump, right? So lithium is 2s1. Once I remove the second electron, that takes a lot of energy. Beryllium has a big jump at the third electron because those are removing core electrons. The core electrons are shown in gray. We're going to get kicked out in a minute. We'll jump back in, okay? How are we doing on time also? Where's my clock? Shoot, I should have got my phone. Anyway, but you can see this trend. So the carbon, I can remove the first 4 electrons, then the 5th one takes a lot of energy. There's a huge jump, and it has to do with removing core electrons. Okay. Okay. I thought we get kicked out in a second here. The atomic size is usually reported as the atomic radius. 1/2 the distance between the centers of 2 bonded atoms, right? So if I have chlorine-chlorine, this distance between the halfway in between the 2 nuclei would be the reported as atomic size. And that shrinks as you go up and to the right. I don't know why they didn't kick me out. All right, can you guys still hear me?
Yeah.
Okay, so as we go up and to the right, we get smaller, right? This is a really nice trend. It's observed almost perfectly. Yeah? Okay. So that's radius. That one's easy to predict. Okay. And it increases as I go down and to the left.